Hey, this is Josh from LeetDev, where we explain programming questions as simple and concise as we can. Today, we'll be talking about the problem Unique Paths 2. In this problem, we are located in the top left corner of a m by n grid, and our goal is to reach the bottom right corner where the star is. And we can do that by moving either down or right at any point in the cell that we're on, and we want to find out how many unique paths we can possibly generate. One extra addition is that there are obstacles in this grid, such as this little gem in the middle, where we cannot traverse. The matrix is represented by zeros and ones, where zeros are all the possible paths you can take, and ones are the obstacles that you cannot pass. Looking at our example, we're on the top left corner, and we have two possible paths that we can take. We can either go right, right, and then down, down to reach the star, or we can go down, down, and right, right to reach the star. We can't go down right because we would hit an obstacle, and so this limits the possibility of paths we can take. This is a classic example of a recursion problem. How do we know that? Well, we start on the top left corner, and we want to either take right or a downward path, and we want to find all unique possible paths to reach our end. Whenever we want to find every possible path of something, that really means that we need to recursively try every single possible combination. And when it comes to recursion problems, there's always a chance that it could be a dynamic programming problem, which is what this is. So a quick example of this, of the recursion problem, is that we want to find a path to our end, and then whenever we find a path, we would just return the value 1, and then we would just add up all the paths that leads up to 1. For example, we can go right here, go down, go right, which is blocked because we're outbound. Then we can go down, go right again, we're also blocked, and then go down. And then we hit our end case. That means we have hit one answer, so we can return 1 back up here. So now we're back at 1, and we have 0 from the right side. And then we just add this number up, and then we can return it back up to our blue, which is 1, and also another 0. I'm not going to go through a full example for this one, but there is an interesting case. So let's say that we go to red, back to red, we go right, and then we go down. Notice how we calculated the answer 1 for this specific cell, and so we will always return 1 because starting from this specific cell, we will go right, which would give us 0, and we go down, which would give us 1. And so we could do the calculation again, but we were smart and we can somehow store the state. We can just return 1 every single time. And then just continue on. Let's say we go down. We can go right, and then we can go down. Down gives us nothing, right returns us 1, and so we return 1 back up. Now looking at this cell now, we know that whenever you reach here, you can get 2 cells back. Now what's really interesting about this problem is, let's say we start from our beginning again and we go down. Let's say we go right and down. Down is nothing, which just gives us 0. But if we go right, we hit our middle cell again. And at this point, we could recalculate everything, but we already know that because we are in this cell, there is only 2 paths we can take to reach the answer. And so that would give us the value of 2. So in the previous cell, we would always have 2 possible paths that can reach an answer if we go down from the beginning. So what I kind of alluded to here is a dynamic programming question where we would save the state of each grid cell that we hit. One flaw in recursion is that we can potentially make the same calculation for multiple cells over and over. For example, if we were to hit the middle cell. Maybe in this small example, it doesn't matter. However, the matrix is bigger. You can imagine that there are multiple paths you can take that would collide with each other, and that would give us an inefficient calculation. As we always do, let's formalize our example. We'll be doing a recursion on our grid starting from the top left corner. The recursive states that we will be changing is our I and j. We will increment our I to move down, and then we would increment our j to move right. There are 3 base cases that we need to be aware of. 1, when our I or j reaches out of bound, as we've seen earlier. 2, when we hit our blocked border, like right down here. And then 3, once we reach our end case, which then we would return 1 back, because that's 1 possible path that we can make. Our recursive case is that when on every cell that we're in, we want to count all the possible paths that we can make by going right, as we've done here. And then count all the possible paths we can make going down, like we did over here. And then once we have all the possible paths we can make on the right side and the bottom side, we just add them up together to get all the possible number of paths we can take from our current grid cell. And that's all there is to this recursive problem. Like I shown earlier in the example, we hit a problem where we might be able to hit the same paths by going to a different location. And then once we hit those same paths, we would do the same calculation over and over again, such as going this way and going this way. And that becomes computationally expensive. Since we're using recursion to solve this problem, we're actually one step away from using a top-down solution, or memoization specifically. The idea of memoization is that we would store the number of paths that we calculate at each grid, because remember, at each grid, we have a fixed number of unique paths we can make that never changes. So whenever we have calculated the value once, we can just reuse it if we encounter it again, saving us the runtime complexity of having to do the calculation over and over. For example, if our yellow path reached the area first, we would store the value 2 inside this grid cell. And then when our purple comes and reaches that same grid cell, instead of doing all that computation, we can just return the value in our grid. The runtime of this algorithm is O of n squared, because before we did recursion, it is a polynomial runtime. But because we are now saving with a certain state that we encounter with memoization, we will only travel through all the grid cells once, because we will have stored all the answers, and that would just give us a n squared runtime. Space-wise, it would also be n squared, because we need to store all the possible answers that we have in each of our grid cell states, and that would give us a n squared storage space. Now let's go through the coding problem. In the coding section, I've already defined some of our helper functions and our fields that we're going to use. For our recursive solution, we define a helper function that passes in our grid, our I value, and our j value, which is the location we are on our grid. I've also defined a memo matrix, which will be used for the memoization part. However, we won't talk about that yet. I'll show you how we can quickly change any recursion problem into a DP solution. And the first step to doing that is just solving the problem recursively. So remember, we have 3 base cases that we need to worry about. When our I or j is out of bound, when we hit a blocked piece, or when we arrive at our target. Now in our recursive case, in every grid cell we are on, we want to explore all the possible paths we can make by going right, and all the possible paths that we can make by going down, sum them up, and then we'll have our answer. And that's all we have to do to solve this problem. However, if we were to submit this question right now, we would hit a timeout exception. I would know, because I tried it. And that's because, like we mentioned earlier, there's a lot of repeat computation that we have, which would make this algorithm have a high runtime complexity. To optimize this problem, we can use our matrix to store all the calculations that we had in our recursive case, and then reuse it again if we encounter it. Essentially, we will be setting it as in our base case. So we need to do a couple things first. First, we need to make sure that our grids have a size of 1, 1. Otherwise, we would crash the moment we define our memo matrix. And then otherwise, we would store anything we calculate in our recursive case inside that specific state that we're in, which is I and j. And then if we ever reach that state again, we would make a new base case where we would just use the value inside our memo matrix and return it. And that's it for this problem. As you can see, this wasn't really that different from the recursion problem. In fact, in the top-down approach, the memoization is the easiest part to solving a problem. The hard part is actually coming up with the recursion algorithm to start with. Once you have that, it's just a matter of using a matrix and then store the values of that specific state and then reusing it in our base as a base case whenever we see it again. Now let's quickly walk through our example. So we start off at the top left corner at I equals 0, j equals 0. Based off our algorithm, we would enter our recursive case and we would increment j, which means we would move right first. At this cell, we still enter our recursive case, so we go right first. And then at j equals 2, we also try going right. And then once we enter there, our j would be 3, and then we would hit one of our base case. Specifically, we reach out of bound, and so we would return 0. And so we go back out of our right recursive function, and we will try going down again. So we go down, and now we're at I1, J2. We can go right again in our recursive case, and that would still return 0. And then we go down, and then we finally hit our base case at I equals 2, j equals 2. And we just return back 1 back up. Now that we've finished exploring our left and our right, we can add them together and then store them in our matrix. I'm not going to draw in our matrix. Instead, I'll just use our current matrix to store our values. In this grid right here, we have 1. And then we go back up at j equals 2. And we see that this value is 1. And so we also store 1 for this path. So at this point, anytime we reach I equals 0, j equals 2, there's always guaranteed to be only one path to the answer. And so we exit our right recursive call and we come back to j equals 1. We explored the right case. Now we need to explore the down case. So we go down, we enter the recursive case, we go right. And now notice that because we have stored the value inside I equals 1, j equals 2, we hit our base case and we just return the value. And so we just return 1 back over here. Notice how we didn't have to explore the whole path. We just knew the answer, and that's a constant time lookup. So after going through the right path, we tried the down path. Recursive case, try going right, we hit our base case, and that returns us 1 again. We go down, which is out of bounds, return 0. And so in this cell, we have a total of 1. Then we return 1 back up, and then at I equals 1, j equals 1, we store the value 2, meaning that from this specific cell, we can have 2 paths to the end. We bring 2 back up into I equals 0, j equals 1, and we know that going right gives us 1, so going through this path, there's a total of 3. We pass 3 back, and then we can try going down from our starting case at 0, 0. We go right, and because we saw that we already seen this path before, because it's inside our matrix, we can just return 2 back as the answer to this path. And then we try going down. Down is blocked, so we return 0. And so now this specific cell is marked at 2. We pass 2 back, and then we have our answer. 3 plus 2 gives us 5. Now let's run our algorithm. Ah, yes, think close. All right, now let's run it for real. Man, so many errors. All right, this should be length. Submit one more time. And there we go. This is how we would solve unique path 2 using a top-down memoization approach. We can solve this problem also by using a bottom-up approach. And if you're interested in that, leave a comment below. Otherwise, if you found this video helpful, consider hitting the like button and maybe the subscribe button to get daily updates. Otherwise, I'll catch you in the next video and have a wonderful day.